Hello, everyone. So, I have a couple goals for the stream today, and I will warn you this will be a little bit longer than my normal updates. First goal is the most important one is to not hit this mic, because as you may know from previous streams, there has been problems with the connection, and at the moment it is connected, and according to my test before I started streaming, it sounds great, but I'm not sure if that will continue. I'm going to keep trying to peer over to the side where I have the volume bar and see that it's still going up to where it normally does. Um, Other than that, my goal is to describe a new. It's not. I don't want to call it a discovery because I feel like it may be something that someone else has already understood, but it is a big breakthrough in terms of the work I'm currently doing, and it may be able to help me kind of push that boundary to something actually usable for what I hope to be doing. So if you don't know what I'm talking about, that project I'm working on is the data mining project. Essentially, it's taking a large multi-dimensional set of data and attempting to create a model to describe that data. Now, whether I want that to interpolate or to do some sort of regression is kind of up to how this works out in the end. But so today I want to talk about first off, I'm going to describe some iterative methods, and then I'm going to describe what I'm currently doing with what I had my breakthrough on. So I don't want to be vague for too long, but I did want to babble a little bit so people could get into the stream. So I'm going to switch it over to a paint window first, just so I can explain what's going on, and then I'm going to actually try and show you some of the code in action that I've done, that I've worked out. So I have some stuff on the screen. I'm not going to talk about it immediately, but down in the corner here, I'm going to describe what these iterative methods I'm talking about. So the first one is Newton-Raphson. I think I was calling it Rapson before. There's actually a PH instead of just a P, so it's an F noise. But I'm going to say NR just for space reasons. So Newton-Raphson is actually a very fast iterative method. And so what an iterative method is it's essentially something you can program into your computer to approximate a value very quickly. And these are very useful tools when it comes to things like reducing error in approximations, because what happens is every time a computer adds, subtracts, divides, or does anything, it propagates a little bit of error along with those transactions per se. So what these iterative methods do is they constantly get closer and closer and closer to the answer, assuming that they converge. And then the reason that that's nice is because even though there is error every time, they're getting closer and closer and closer, so that error approaches a very small number. So obviously, you can't get to the exact answer this way, but you can get pretty close, and you'll get enough significant figures that for whatever you're doing, you'd be satisfied. So Newton-Raphson essentially what it does is it looks I think I described it in a previous stream. I'll try and link that, but it essentially what it's used for is finding zeros of a function. So if you have, let's say, a parabola that went down, kisses the x-axis, and so this is the x-axis and this is the y-axis, and so we're saying that that touches here, and um, we want to find this numerically with a computer. So what we would do is, so the Newton-Raphson formula is a way of improving upon a guess. And the way it does this is by the algorithm xi plus 1 is equal to xi minus the value of the function at xi over the first derivative of that function at xi. And so essentially what this is doing, because that may seem a little bit vague, is let's say we guessed a point here. What this algorithm is doing is it's essentially setting up a tangent line. So I'm going to get a different color here. We'll get some red. And it's looking at the slope of this line right here. And so this goes off in both directions. And so what this does is it goes and it looks at the slope, and then it finds where that tangent line hits the x-axis. And where that tangent line hits the x-axis, it then picks that x as the new guess. So this would go up to the line. This is our second guess. Now this is a much steeper slope. I'm just going to get orange because we're getting a little closer. And so you can imagine a tangent line like that. And then we have a second point where it hits the x-axis. So I don't know, I'm going to go light blue. That's probably not going to be very visible. So we go up to where that is on the function and keep doing that. And what this does is it slowly gets closer and closer and closer to that zero. Now, there are situations where it can get stuck in loops, and there are situations where the algorithm itself just doesn't converge. So the reason that this is very nice in computers is because it converges quadratically, which means it converges extremely fast. Most things converge linearly. In this case, well, so if you were just taking the bisector between 2 points, seeing if it's positive or negative, and then moving in the direction and taking another bisector of that smaller point, that would converge linearly. But this algorithm converges extremely fast, and so we'll get to how fast that is in a bit. Um, but I want to explain to you one more algorithm. So I'm going to kind of clear up some stuff here and get some rectangles and cover up everything. Okay, so um, so also, if you're watching and you notice anything that I've mentioned that you disagree with, or if you notice something I'm not mentioning, please post that in the chat. I'm just trying to do a quick summary of these iterative methods. So another iterative method is the steepest descent method. And so steepest descent is a similar method to Newton-Raphson in form of algorithm, but it's somewhat different. So what we're doing is it's actually xi plus 1 equals xi minus some delta x times your derivative. So that would be, I guess that doesn't really matter if it's xi. And then xi f prime. Okay. So this is the algorithm for steepest descent. So what it's essentially doing is it's checking what the slope is at that point. It's um, it's going in the opposite direction. So what this is essentially in terms of a multidimensional system is that this is the gradient. So it's going in the opposite of the gradient. The gradient is essentially like if you had a terrain that had a mountain, then and you're here, obviously the steepest way, the steepest direction would be straight up the mountain. So steepest descent means that we're going as fast as we can down the mountain. So if we have a point like this, and we have our parabola again, and we pick our guess out here, what this is doing is it's looking at the slope, and it's going, so it's looking where the slope goes up and going a tiny step in the opposite direction. So we're going to keep working our way down here, delta x by delta x, and eventually we're going to get pretty close. And so you could miss this by a little bit, bounce back, but you want to set your delta x based off of how willing you are to pass it by a little bit. So this method also is very viable, but you'll notice it takes a lot more steps to actually get there, depending on your delta x. But obviously, if you picked a large delta x, there's a higher chance that you'll miss your answer. So there's some things to mess around with this. But the cool thing about steepest descent is it's very it's pretty consistent in its getting to an answer. Now, there are some problems. So let's say we had a different function that I'm going to draw in maroon that has the same answer. That's probably not standing out too much. But then it has a second divot right here. Well, if you get to this point, then it will, if it takes one step in this direction, then it will want to go back down into the hole. And if it takes a step into this direction, it will want to go back down into this hole. So it will never find the true answer. And so this is a problem, but what a lot of people do is they'll use steepest descent to get to a guess that will be able to be plugged into Newton-Raphson. And then Newton-Raphson will get to the actual answer immediately. So Newton-Raphson will just jump there in a couple steps. So that's essentially a quick summary of iterative methods. So I want to get to what I'm doing with these, and so this isn't necessarily the normal way of using these methods. I did talk about using a Newton-Raphson or something like it to take the equations that the AI was making and make them better. But I realized that didn't really, although it did make the equations better, it was causing some problems because it was perfectly lining up the lines through the data, but not necessarily pinpointing the data. So in that case, I kind of wanted it to interpolate. But so I'm going to get to what I have on the screen here. So just to give you some background, my AI, what it does is it currently the deep learning aspect of the AI, every iteration creates new pieces of a function. So what I mean is there's a bunch of variables. So let's say we have 10 variables labeled 0 through 9. So that would be, let's just say A, B, C, D, or I guess I could call them X of that number or whatever. So we have our initial input variables. Now, when we're trying to figure out if we're trying to predict for the 0th variable, then if we're trying to predict the 0th variable with the rest of the variables, then we need to find the relationships between these variables. Now, the original AI, without the deep learning, would just try combinations of them by multiplying, dividing, and all this wonderful stuff, and it would get closer to the answer, but the problem is it was very slow, and a lot of times it would stall out because some of the bad equations would get lucky with the data. So I added in deep learning, and what deep learning does is every time there's a mutation, it has a chance to create a new combination of these variables that can be used just like another variable. So we'll have variable index 10, which would be, I don't know, x1 divided by x3. And so there's just different combinations that are created randomly. And so this part of the AI is very good at creating random combinations. And what I wanted to do was to set up a new format for the AI, not necessarily evolutionary. There will still be some evolutionary aspects in figuring out how many things it needs. But let's say that the function that we have, like this one, is x variable 2 plus x variable 0 squared plus x variable 2 to the power of x variable 0. So that isn't using a lot of these variables. But if the deep learning mutation can create these combinations where we have x squared, we have a variable that's x squared, and we have a variable that's z to the x, or x variable 2 to the x variable 0, then we can, sorry, we're trying to approximate zero, so this might get a little confusing, but um, it can create these combinations, and then I wanted to create an algorithm that would combine these linearly. So it's a linear combination, it's just adding them together. That's all it is. But if it has all these variables at its disposal, then why can't I use something like Newton-Raphson or Steepest Descent to find the best combination of those given variables to approximate the answer? So that's what I'm essentially doing. And so, but it's a little bit different how this works. So this is where I get into what I have on the screen here. I'm gonna um, color back this section just so it's not getting distracting from the graph. Um, okay, so I have this graph here, and so what I'm essentially doing is I'm setting up a graph of this function a. What this function a is that when you when you plug a number into a, you get back the answer of that particular data point, which in this case we're using x is equal to x0 is equal to 5, x1 is equal to 9, and x2 is equal to 2. Um, then it will go in and look at which variable is in that index spot, and it will then it will plug in the data point to the function that number is that index is associated with, and spit back out the initial function, or spit back out the answer with that data point. So what I'm essentially doing is I'm creating a series of these functions. So I'm going a0 plus a1 plus a2 in this case, because there's three things we need to work out. Now, obviously, the AI won't know that immediately, but if there's only three, it should get there pretty quickly. But I'm going to make this more of a general case when I go to code this in the future. So in this case, we have an A0, an A1, and an A2. And so I need to create an algorithm that will figure out which of these functions need to be put in place of each of these placeholders. So what would happen with Newton-Rapson is you can actually use that to solve a system of equation in multiple dimensions. What you do is you set up the normal system of equation into a matrix form. So you'll have matrix A times vector of the variables x is equal to vector of the answers b, and so you can bring this out into as many dimensions as you want, and it will still provide you with an answer, assuming you set it up correctly. So what I wanted to do is I wanted to approximate the index that is necessary to be plugged into each of these three functions in order to combine to create the actual function we're trying to approximate. And so what I did is I thought about it this way: if I set up the answers to this function based off of the number on a graph, then if we have 0, 1, 2, 3, 4, 5, and so on, then what we can do is actually just say that any decimal number between 0 and 1 is 0. And actually what I think I'm doing is not actually that, it's rounding. So we're doing this, we're doing this. So it's a stair-step function. And so this would normally cause problems because there's discontinuity, but what I found out is that as long as you arrange the indexes to coincide with the functions that you have in a particular ascending order. So when you plug in this variable to these, you'll notice that they go up in value each time. So we have 2, 5, 9, and then we have 4 times 9, which is 36. We have 2 to the 9, which I believe is, I want to say that, no, sorry, 2 to the 5, which is 32. So I think I actually have those backwards. And then I have these all mixed up. 5 squared, and then I have 5 times 9. But what I'm saying is that if you order them in ascending order, so not the way that I've done this, I think I was actually working with a different data point previously, and I tried to bring it back for the stream, and I forgot to reorder these. But what happens is it will actually be able to plug in and find the answer. And the way it does this is by saying that 0 is equal to A0 plus A1 plus A2 minus F. And then, so you find out, this is the function we're working with. So we're saying that this is going to be, I don't know, G. So G is equal to this function. And we're plugging G into the Newton-Raphson or steepest descent. So we say that A0 is equal to A0, which is the previous A0, so encoding it technically works out, minus our G over G prime. Now, when I plug this into a program, I'm not doing anything symbolically, so in order to do the derivative, I simply did a central difference. So I did G plus, so it's, I'm gonna draw this a little smaller, I guess. So this is gonna be G of our X, and X, remember, is all of our variables. And then G of X, but the particular, actually, sorry, I'm doing this wrong. So G is going to be based off of our A's. So F is going to be constant because at this particular point it is a constant. Whenever you plug this point into our actual function, it's the same. But G of our A, I'm actually going to write it out. So A0 plus, oh, sorry. I'm a little messed up at the moment. A1 and A2. And then our central difference would be G of A0 plus some delta A1 and A2 minus the same thing, so except this is a minus sign. So I'm running out of space here, but so it's G minus and then all over 2. So what this is essentially doing is, let's say you had a curve like this and you're trying to find the instantaneous slope at this point. We're essentially taking a step forward and a step back and making a secant line. And so that's a pretty good approximation, especially if your step is fairly small. Now, in this case, that's not what I did. In this case, I actually made delta 1. And the reason I did that is because if the delta wasn't 1, it wouldn't make any change in the answer. So what I wanted to do was, say you're here, say that A has chosen 2, A0 is 2. Then for this case, it would go back to 1 and it would go up to 3 and it would get the point between those. And so that's not the best approximation, but it is in the right direction always because I have put this in ascending order. Now, I would imagine this would still work in descending order. I have not tried that, but this does work if you order the functions that you're indexing in ascending order. And so what this essentially does is it finds out uh, if this particular function needs to be less or more in order to get closer to having g equals 0. So obviously g equaling 0 means that we've minimized the difference between our function and the actual function. If g equals to 0, then our function is the actual function. Um, so that's what I'm doing in the code. And so I also implemented this with Steepest Descent. All this is changing this algorithm um, to, instead of having this on the bottom, we get rid of this. We just have the derivative, and then it is actually multiplied by a small number um, because we don't want it to overshoot. So uh, so we have our central difference times zero point 0.1, and so it's taking tiny steps towards the correct answer. So I'm going to try and show you both of these codes, and then we'll get into what I haven't been so successful with. So let me get one pulled up. We're going to start with Newton Raphson and sort of explain its benefits and its flaws. So let me get that running first so it shows up on the screen, and then I'm going to switch the screen to that one. Okay, so you see my Python shell up here on the left, I believe. So what I'm going to do is I'm going to give it a guess. Now remember, our data point is 592. So I know that for the guess, because I've been testing it out, for the guess 444, it is successful very fast. And by very fast, I mean it took 3 steps to get to the answer. So what I'm doing, I should probably mention that, is if you look at the paint window, I'm actually rounding to the nearest integer and applying that as if it were the index in A. So that's an important note. So it's not necessarily getting the exact answer that fast, but it's getting a number that rounds to those indexes. And since it rounds to that, and we've tried those particular rounded indexes, and it creates the function, there's no point in attempting to get closer to those answers because we do have the answer. So it figured out what the answer is. Now, these are the indexes of the functions that are the variables we're working with. So if you remember from the paint window, now my face is actually over top of it. Let me see if I can move that slightly to the side. Okay, so that was our function, and it should match up with what we have here. Now, I remember, like I said, I mixed up some of the variables, but it seems that my code is still working, so I'm pretty sure I don't have them mixed up in the code. But so I want to show you the steepest descent. So actually, let me first show you the flaws with Newton Raphson. So I'm going to pull up Newton Raphson again, start it up, and we're going to pick a bad guess. We're going to say 1, 1, 1. And so this isn't the answer we want. And actually, that might be. I remembered when I was messing around with this, there actually ended up being another answer that was correct. So I'm going to just rerun it again and pick a different bad guess. Let's do 2, 3. Sorry, I can't. I gotta enter between each one, and that got to the answer. Okay. I'm trying to show you a bad guess because it does go crazy. It's spot on right now. All right. I'm not sure because I was testing this before. I don't know what I changed, but it's actually getting to the correct answer every single time. That's the other answer, and then I don't know. One, two, three. That's the right answer. All right. Well, so the problem with Newton-Raphson is it tends to blow up, and so I don't know if there's a bad guess I can give it because there's only so many guesses. I don't know. Let's go 999. Those, yeah. So those aren't even indexes, so I can't do that. Um, but so what it does initially is it tries the problem. It tries the guess that you gave it to see if it's correct, and then um, moves on from there. So um, I want to show you the steepest descent. So I guess you'll just have to take my word for it that the Newton-Raphson tends to blow up if you don't go fast. Did I close out of the paint window or something? Yeah, I don't know what's going on with that. I think my screen capture software is screwing up a little bit. But all right, so if we have steepest descent up and I pull that up, then I should be able to show that to you. I'm obviously the paint window is screwing up for some reason. But so we're gonna start out with the same guess we did 444, and it's not getting to the right answer. I'm sorry for the technical difficulties here. I'm not sure what's going on. Um, I don't know if it has something to do with my computer glitching up right now. But I'll give you a recap of what was going on because I'm not sure what changed. So the Newton Rapson was taking about three iterations, maybe two in some cases, maybe five in some cases that were particularly far away. But all of them were very small amounts of iterations. Now, the steepest descent would more consistently get to an answer, but would take around 26 iterations, maybe 13 in some cases. I don't know why those numbers specifically, but like I said, there weren't many guesses to make. Um, so the steepest descent would more consistently get to the answer because it just continually takes steps in the right direction. And in the case of what I was working with, there were technically two correct answers, so there could have been another spot that it would get to, but it was pretty good at getting to an answer. And so that's what's great about Steepest Descent. And as you see, it went through 1,000 iterations that fast. So in terms of speed, it's not really a problem if it takes a little bit longer, but gives you a little bit more consistency. So that's where I was successful. And so I'm going to actually try and pull up the paint window again, see if it's all right. It's working with us. I think there was a problem with it closing out and then going up while the program was running. Um, okay, but I'm going to clear the board here. And so now I'm going to get into where I want to go with this. So I've been, like I've said, I've been working on the data mining project, which is essentially trying to model a large sum of multidimensional data. And what I mean by multidimensional data is that there are many inputs trying to predict one output. So then the AI has to work through, find the connections, and then procure some sort of model in the form of a function where if you plug input variables in, you get a approximation of the answer. So I have had some success with this in the past, but everything has been extremely slow. Now, these iterative methods are well known for being very fast. And so what I wanted to do was to try and implement these iterative methods in the form of running these iterative methods to find the best solution out of the possible solutions the AI has procured with random combinations. So this would kind of take away some of the randomness. Now, obviously, there's going to be some randomness because the AI still needs to create these combinations. And we don't want it to be, we don't want it to try to create every combination because there's infinite combinations. Some could have double variables in it, and so it would go crazy. We want it to create combinations and then be rewarded for good combinations. So that's how the evolution the evolutionary process will still be in there. The combinations will only be kept if they are used previously for a best function. Um, so that's what I've been working on. And so I attempted to implement this idea of using an iterative numeric method to predict the the optimal combination of variable pieces of variable combinations in a linear fashion. So to create our function f of a 0 a1 dot 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 an. So this is our function we're trying to create to approximate our f of x y dot dot dot. You know what I'm talking about. So uh, what I was trying to do was to use this to essentially create a linear regression. Now, there came a problem with this because in the previous uh, running, where it was a simple situation, there was one data point, there was one equation. Obviously, there's still one equation, but there was only one data point to work with. That's the main point. We could just easily bubble sort these these a values based off of an index being put into them, into an ascending order. The problem with a range of data is, let's say our function our function here was x squared, or now let's make this x cubed actually. So x cubed, if you know what an x cubed function looks like, it comes up from the bottom left, goes up, passes through the origin, and goes like this. So let's say that we actually shifted this to the side a bit, and we have this function being part of our data. So let's say this a value is called x cubed has some error over the well, obviously we're trying to get to some f value. X cubed has some points over the x-axis and some points under the x-axis. Now, we could have another situation that's negative x cubed. And what this would do is it would just be the same thing except upside down. And the problem with this is that these have the same least squared distance from the answer. All these points end up coming to the same distance and total area in between. But they cancel out. These would, if added together, would be 0. But if you add their least squared regression together, it's greater than 0, because both of the least squared regressions will be positive. So this became problematic because how do I put one to one side or to the other? And how do I say that if I add this variable to this function, it will go up instead of down and whatnot? So it became a little bit more multi-dimensional in a sense when I added more data points. And so this is something I've been tossing around in my head, just trying to figure out how to deal with it, because obviously I can't just go to a straight linear squared regression, because there's going to be situations where things would cancel out because of their negative values and whatnot. Even if the values are like this, like we had a cosine function, or that'd be a sine function actually, and then we have the opposite, then it's still going to have some regression from the actual value. But if we added them together, they would actually be the actual function, or the function value we're trying to get to. So this is something that I've been tossing around. So if there's any suggestions from people watching this, I'm very open to working with people because I really don't think that. Well, I'm gonna keep tossing this around, but this may be a little above where I'm at right now. So I'm not sure, and if there's any suggestions, I'm very open to them. But other than that, I guess I'm going to open the discussion up for questions if there are any. I see we have a few people watching live. Um, so I've been talking for about 40 minutes, which is pretty long for one of these updates. But I hope that this has. I hope that I've done well to explain what I'm doing here. So I'm just gonna give a quick summary while I wait to see if there's any questions. Um, so I went over iterative methods, and then I went over how those iterative methods could be used to pick out the optimal pieces of an equation. So I said that I figured out that it works if you put those pieces in ascending order, and then I showed you how I showed you the programs running. They didn't work the way that they did before I started streaming, so I'm not sure what happened. But um, and then I told you how um, because there are more dimensions to a graph as opposed to a pinpoint of data, then it becomes problematic because the regression from that line doesn't necessarily um, add up. I guess it's sort of like intensive and extensive, I guess, if you can think of it that way. But it matters which direction the error is in, but at the same time, it only matters at that particular point. So I'm not sure how I'm going to play around with this. I don't know if I'd be able to sort of approximate the function at each point. That was an idea I was throwing around. Pick a bunch of points, approximate the optimal function at those points, and then look and see which function was used the most, which combination was used the most, and find the mode of those combinations, and just say that's the best one. Maybe test it a little bit more to see if it actually fits all of the data. Also, I've been also throwing around the problem with when it comes to actually just finding the best option, even if it isn't the final answer. Because obviously, if this function has three terms and this guess has two, or even it could have four, that would still be problematic. Um, then, if it doesn't have the right amount of terms in it, how do I pick a function that is not getting to zero, but is getting as close as it can with what it has to work with? So that seems like an easier question, but I can't really solve that until I have a working program to solve for zero in the first place. So other than that, I'm not seeing any questions. Obviously, if there's any questions when you're watching this later, I'm very open to them. I'm going to be posting this on Reddit forums and trying to get some views on it because not particularly getting views. I just want to get this specific topic out to find out if there have been people who have done something like this, and also if people have suggestions on how I can continue from where I'm at right now. So I want to thank you guys for watching, and I'm not sure if I'm going to be able to stream on Saturday. I have a lot going on, but I do think that I will be back on Sunday. So let's aim for Sunday and keep an eye on my Facebook. I do have some good topics planned. Like I said, I want to make up for not being able to stream last weekend. But other than that, my voice is getting pretty shot, so I'm going to be signing off. So I will see you